Hi, hello everyone, and welcome to the reinforcement learning tutorial. As you can see from the title, I'm going to take you from the foundations of reinforcement learning to the state of the art. Now that's a challenging task to do in 45 minutes. However, I hope that I succeeded to provide a good balance between math and intuition, and I hope that by the end of this talk you'll take home with you at least the understanding of what is RL, what it can do, and what are some core techniques that make it work. So I think I can skip my background because thanks to Nathaniel, but I would just say that currently I'm in GM. I've been a group manager, co-founded the autonomous driving group, and also applying reinforcement learning for challenging problems related to the future of transportation. My past research projects focused on making autonomous agents learn and act in realistic environments. My dissertation, for example, focused on autonomous trading agents that trade energy for the benefit of a smart electricity grid. Additional projects included applying reinforcement learning to control a smart thermostat to save energy, applying reinforcement learning for 3D simulated robotic soccer and autonomous ship navigation. So let's start by asking, what is reinforcement learning? So here is Rich Sutton, probably the founding father of reinforcement learning, or RL. And according to Rich, RL is agent-oriented learning. It's learning by interacting with an environment to achieve a goal, where learning is done through trial and error with only delayed evaluative feedback called reward. For those of you who know supervised learning, where we give correct examples or labels to the learner, in reinforcement learning, no one is telling the agent the correct decision, but only this evaluative feedback called reward, which we will see later what it means, roughly telling how good the current action is. One nice feature of RL is that learning can tell for itself when it is right or wrong. It doesn't need supervision. And in general, reinforcement learning is considered a kind of machine learning that is most like natural learning that we can find in animals and perhaps in humans. So when getting into a new domain, it's always good to start with an example. And the examples I'm going to show you are from the RoboCup domain. RoboCup is the World Cup in robotic soccer. Was established in 1997 and has today hundreds or even thousands of participants. RoboCup has several different leagues. I don't know if you can see my pointer, but starting from the bottom right clockwise, there is a 2D simulation league, 3D simulation, small size, medium size, and standard platform, as well as several other leagues. And in RoboCup, one of the subtasks is called half-field offense. So in this task, a team of simulated robots, in this case the red team, is trying to score as many goals as it can against a team of defenders, the blue ones in this case. And what you see here is a random policy executed by the red team. At every time step, a simulated robot selects randomly among kicking, passing, or dribbling. And as you can see, this behavior is not very effective, so obviously we want to improve it. So one way to go about it would be to hand code a better policy into the red team. However, frequently it's better to use another alternative called reinforcement learning. So here is my colleague and friend Shivaram Kalyanakrishnan, did his PhD at UT and currently a professor at IIT Bombay. And during his PhD studies, Shivaram trained simulated soccer robots. And the way he trained them was as follows. Shivaram is telling the robots that it is desirable that the ball be in a position that is inside the goal, and ask them to go figure out how to make that happen. And indeed, Shivaram sends his robots to train on a cluster, on a computing cluster, to figure out how to make that happen. And several hours later, the robots become with the following behavior. So we can see that this behavior is much better than the previous one, and the team learned to score goals that involve some complex coordination, finding holes in the defense, and scoring under tough conditions. And again, I stress that no one programmed this behavior into these robots. They were learned completely through trial and error in simulation. Okay, let's see another example, this time from the 3D simulation league. So here we have a physical simulation with friction and gravity, and we start by hand coding a humanoid robot walk. And as you can see, this walk is pretty stable, but is very, very slow. Again, we use reinforcement learning. We send the robot to train on a computing cluster, and several hours, the robot returns with the following walk. And we can easily see that this walk is much faster, is still stable, and is able to take a ball all the way to the goal. And this was one skill learned using reinforcement learning. We actually use reinforcement learning to learn several skills. And in fact, this skill learning process was the secret sauce behind winning several world championships. And I prepared a short highlight video for you from one of the recent competitions. So for example, in this case, we are the orange team, and what you're seeing, for example, this kick was learned using reinforcement learning. The robot's movements, and some of their coordination was learned using reinforcement learning. Again, we didn't program all of these behaviors. And please pay attention to this play. So in this league, we have the parallel of Intel's 3D multi-angle technology, as you can see now. And this was one of the nice goals scored in that competition. So what did we just see? In the above examples, we didn't program behaviors. Instead, we wired a performance measure and let behaviors emerge through reinforcement learning. And an important point to remember is that reinforcement learning applies to any problem that involves optimizing sequences of decisions over uncertain outcomes. Scientifically, reinforcement learning overlaps with several other fields, obviously computer science, but also engineering, mathematics, economics, and even psychology and neuroscience. And recently, RL is also transitioning from academia to industry. So in 2017, MIT Tech Review ranked it among 10 breakthrough technologies. And I cite, by experimenting, computers are figuring out how to do things that no programmer could teach them. Okay, so what can reinforcement learning do in these days? I collected several successful applications. For example, from the domain of robotics, reinforcement learning was used to teach robots to walk, to teach autonomous helicopter to fly challenging maneuvers, and also to teach complex manipulation skills. Some of them we'll see later in this talk. In table games, reinforcement learning programs were able to be top humans in a complex game named Go, and in the game of poker. And in the domain of computer games, reinforcement learning programs were able to learn and achieve human-level play in tens of Atari games, and also in complex real-time strategy games such as Dota and StarCraft. And this complex real-time strategy game requires both long-term planning and short-term execution, and the performance of the RL programs is pretty impressive. Okay, so now that we know that RL can do some nice things, let's see how it works. And for that, we'll need to get a bit more formal. So each scientific area is defined by a research question. What research question defines reinforcement learning? In that context, we think of an agent interacting with an environment, where the agent senses the environment, executes some thinking or decision-making process, selects an action and executes it in the environment. And then the environment progresses, and then this loop repeats. More specifically, the agent gets from the environment some representation of the state of its surroundings through its sensors, and also this reward signal, a numeric value that tells it how good the current state or actions are. And in this context, the RL question is, how must an agent in an unknown environment act so as to maximize its long-term sum of rewards? Let's get a bit more specific. So reinforcement learning problems frequently are defined as Markov decision problems or Markov decision processes, in short MDPs. An MDP has a set of states, in this simplified example 10 states representing the possible states of the environment, of the surroundings. And in each state an agent can take actions. In this case, in state 1 the agent can take the green action and move to state 3, or it can take the red action and move to one of several states according to underlying probability distribution. And same thing holds for all states. One additional component is the reward, evaluative feedback. These numbers assigned to each state telling how good it is for the agent to be in a given state. So for example, let's see an example. So an agent starting in state 1, taking red action, moving to state 2, getting a reward of -1, then taking red action again and moving to 6, getting a reward of 2, and then take the green action, getting 10 and moving to 7. And this is how the life of an agent looks like. It's a possibly very long trajectory of being in a state, taking an action, getting reward, moving to the next state, and repeat. And the goal of an RL agent is to maximize the expected sum of long-term rewards with a minor modification. We discount, if you notice, by gamma between 0 and 1, we discount the future rewards. The goal is to encourage the agent to get rewards earlier rather than later, and this obviously also helps the math, otherwise it wouldn't be there. Okay, so in an MDP, a deterministic policy is a function that maps state to action. So a policy pi getting a state S outputs an action A. So when we say an agent is following a policy, this means that when the agent is at time t in state st, it applies the policy function pi to get the action at and then executes this action. On the top right, we see an example of a very simple policy that tells the agent if you're in state A, take action 2, if you're in state B, take action 1. And I should also note that the number of all possible policies is exponential in the number of states. And what an RL agent needs to do is to search for a good policy in this usually very large space of policies. Okay, an important concept is an action value function. An action value function says how good it is to be in a state, take an action, and thereafter following policy pi. So the action value function is denoted as Q for a policy pi, and for a given state S and A, this is the expected sum of future rewards. On the bottom left, we see an example for an action value function. For every combination of state action in this small two-state MDP, there is some value, which is the expected long-term sum of rewards. And just by looking at that, we can immediately see that when the agent is in state A, it's better to take action 2 because it has higher value than action 1. And when it is in state B, it's better to take action 1. A policy is considered optimal if it maximizes the action value function over all possible policies for every combination of state action. Therefore, all optimal policies share the same optimal value function. And also, given the optimal value function, it's very easy to act optimally. How do we do that? In a given state S, we just scan all the available actions A, and just execute the action that maximizes Q, the action value function. So we say that the optimal policy is greedy with respect to the optimal value function. We call it greedification. And in a Markov decision process, there is always at least one deterministic optimal policy. Okay, so in the rest of the talk, we are going to see how RL agents find approximately optimal policies by starting from small known environments, then moving to small unknown environments, and finally moving to large unknown environments. And we'll see examples of RL in action throughout the talk. A few notes or clarification. When I'm talking about an environment, in this context, it is an MDP. We assume that the MDP captures everything the agent needs to know about the environment. When I'm talking about a small environment, this means MDP with small number of states and actions. And when I'm talking about a known environment, this is MDP with known reward and transition distributions. Okay, definition, solving an MDP, meaning finding the optimal policy. Exact solution methods can solve small and known MDPs by computing optimal value functions using Bellman equations. Bellman equations introduced by Richard Bellman, and they define recursive relationship among values that can be used to compute values. What do I mean by that? In brief, what the Bellman equations tell you is that if you want to be optimal, start by taking the right action, and then step 2, keep being optimal. How does it work? We can look at a web of transition dynamics defined by an MDP. So here, each white node is a state, and each black node is an action. And an agent can start from some state, take an action, move to the next state, take another action, and so on. And we say that the agent is going through a trajectory in the state action space or in this web of transition dynamics. And if we take the current state as a root of a tree, we can put all possible future trajectories to create a tree of transition dynamics. And when we want the agent to act optimally or to act to maximize its expected long-term sum of rewards, the expectation is over all possible future trajectories. So naively, we would enumerate all these trajectories and compute an expectation. But thanks to the Bellman equations, we don't need to do that. So the first Bellman equation is Bellman's expectation equation. I'm starting from the definition of Q values that you have seen earlier as the expected sum of future rewards when following policy pi. And when we stare at this equation long enough, we see that the part underlined by blue is actually the Q value in the next state and action. So that is the recursive relationship between the Q value in the current state and action and the Q value in the next state and action. Graphically, we can show it using this diagram. So the root is an agent being in a state S taking action A, and then the agent can move to one of several possible next states. Can you see my pointer, by the way? Yeah. You can move to, apologize for, I hope you guys see it as well. I'll try to balance it during the talk. It can move to one of several next states, and then from each state there is an action dictated by the policy. So if we know the Q values of the bottom layer, then we can, and we know the distribution of next states, we can compute the expected sum of future rewards. And this expectation must equal the Q value at the root. The second Bellman equation is Bellman's optimality equation. This is the same equation as the first one, only for the optimal policy. So obviously the first equation holds for the optimal policy because it holds for any policy, but we also know that the optimal policy is greedy, is maximizing the Q value, and therefore we can put the max operation directly into the equation. And an optimal policy must satisfy this equation. And if we are able to solve this equation, we get the optimal Q values. What do I mean by solving the equation? The unknowns here are the Q values for every state action combination. So we have, imagine a large vector of Q values that we are trying to find from this set of equations. And if we are able to solve it, then we have the optimal Q values. Again, we can describe it as a similar diagram, only that we have a max operator at the bottom. And this is where I meant that to be optimal, you need to take a first correct step and then keep being optimal. This is the part underlined by blue. Okay, so to solve MDPs, an important step is called policy evaluation. Given a policy pi, any policy pi, policy evaluation computes the Q values for policy pi. And it does so by solving Bellman's expectation equation, which I put here again for the reference. There are many ways we can solve this equation. One of them is an iterative process. We start by initializing Q values to 0 for all combinations of state actions. And then we repeat until convergence to compute the right-hand side, the expectations, the right-hand side of the equation, and then assigning it using the current estimation of Q, Qi here, and then assigning it to the left-hand side to get a better estimate of Q. And if we repeat it long enough, this process is guaranteed to converge to the Q values of policy pi. Going back to our diagram, we can see that if we have graphically, what it means is that the right-hand side of the equation is an expectation over these nodes, expectation over next possible states, and the Q values that the policy induces. And if we are able to compute these, then we assign them to the left-hand side, which is the Q value at the root. And this gives the name backup diagram, because we back up value from the bottom to the root. And we do it for every combination of state action, not just one. Let's see an example of policy evaluation. So here we have a fire maze with two robots. Each one has its own policy. One is always go forward, and the other one is always go right. How do the Q values look like for these policies? So if this is how they look like. So for both policies, if we're in the goal state, the top, they get a reward of +100. And if they're in a fire pit on the side, they get -10. The differences in the Q values here, which for the go forward policy are just 100 discounted by the number of steps to the goal, while for the go right, it is -10 discounted by 1 step. Why do we care about policy evaluation? The reason is the policy improvement theorem, which says that given the value function of any non-optimal policy pi, we can always create a strictly better policy pi prime as follows. If we have the Q values for pi, then pi prime at a given state S will execute or select to execute the action that maximizes the Q values computed for the old policy pi. In this case, the definition of a strictly better policy is that for every state in the state space, the Q value for the action dictated by the new policy is at least as good as the Q value for the action dictated by the old policy. And for some states, it's strictly better. So this gives us a way to get better and better policies. We can, the way to do so is by repeatedly alternate policy evaluation and policy improvement. So in the right-hand side, you can see an example of, or illustration of how it happens. We can start from any random policy pi1, run policy evaluation, compute the Q values, and then run policy improvement or gridification to get a new policy, then evaluate the new policy and improve it, and so on, and this process is guaranteed to converge, and typically after only a few steps, and converge to the optimal policy. This process has a name, and it is called policy iteration. Policy iteration converges very robustly under a variety of conditions, including incomplete improvements, incomplete evaluations, asynchronous updates, and randomization and noise. For example, we don't need to run policy evaluation until convergence. We can stop earlier, and we don't need to run gridification for every combination of state action. We can only run for a subset of them. As long as we make some progress in evaluation and some progress in improvement, the algorithm will likely converge. So therefore, there is a more general version of policy iteration called generalized policy iteration, which defines any interaction between a policy evaluation process and a policy improvement process. And the reason generalized policy iteration is important is because almost all RL methods that you might encounter are some instances of GPI, generalized policy iteration. Let's see an example of how it works. So here we have a different maze. The goal is to get to the top right cell while avoiding the middle right. And we initialize all Q values to 0 and initialize the policy to always go up. And then we run the first iteration of policy evaluation, so we get the reward at the goal state to be -1 and the other state -1. And as we continue this process, the values propagate throughout the entire state space and their estimations are refined. And eventually, this process converges to the optimal Q values, which are the numbers here, and to the optimal policy, which are the arrows. The optimal policy tells the agent from every cell here what the optimal action to take. Okay, so we've seen that generalized policy iteration finds an optimal policy in a known MDP. Where do we use the fact that we know the MDP? The place we use that is that we assume that we know the next state distributions, P, and the reward distribution, R. we assume that we know the probabilities that given the agent taking an action, what's the probability distributions of the next state. We use it to compute these expectations as the right-hand side. But what if we don't know these distributions? And in fact, this happens in many real-world problems. You can think of a robot that is deployed in an unknown environment. It doesn't know the environment dynamics. What do we do? So in that case, value-based RL methods overcome this issue using three key ideas. The first one, they still seek to estimate value functions like we have seen. And the second one is that they also execute generalized policy iteration that we have seen. But the main difference is that since they don't have knowledge about distributions, they just need to use collected experience instead to represent these underlying distributions. So going back to the tree of transition dynamics, okay, so let's start from the bottom right. A naive approach that I mentioned is enumerating all possible future trajectories to compute values. We have seen that Bellman equations saves us the need to enumerate. That's the top right. And Bellman equation is, by the way, a dynamic programming method. This saves us the need by backing up values one level up. But it assumes that it knows the distribution of next states. At the top left, when we don't have the distribution, we just can take one example of or one data point of interaction with the environment. The agent is in some state here, taking an action and moving to the next state. And we can use this one example to do a backup of value from the bottom to the top to get an improved estimation. And when we do that, this is called temporal difference learning. And this process also converges, as we will see, to optimal policies. And we can also do multi-step backup with the bottom left, which is called Monte Carlo backup. Okay, so let's go back to our small MDP example and assume that we don't know these transition distributions. So we can execute some reinforcement learning algorithm. In that case, Q-learning, probably the most famous RL algorithm. And the way Q-learning works is by maintaining a table where the rows are all the possible states, and the columns are all available actions. And I remind that we're talking about small MDPs. This is why we're able to enumerate them. And every cell in the table is the current estimate of the Q value of the optimal policy. And Q-learning updates this table from interaction data with the environment. The way it updates is using this one-line formula, which I won't get into here, but in general, the current estimate is updated towards some target value by some fraction amount alpha between 0 and 1. And if you look carefully, you will find, again, generalized policy iteration behind Q-learning. The max operator is policy improvement, and the entire computation is policy evaluation. And the amazing fact is that as long as a Q-learning agent acts greedily based on these estimates, meaning that at any point in time it selects the action with the highest estimated Q, and make sure to select enough times suboptimal actions, because there might be some action it doesn't have enough data about to know their Q values. As long as it does that under some minor conditions, Q-learning will converge and induce an optimal policy. And this was proved by Watkins and Diane in 1992, and this in fact opened an entire research field known today as reinforcement learning. Let's move to large unknown MDPs. So where are we now? We defined the RL problem and modeled it as an MDP, and we saw that for small known MDPs, generalized policy iteration can find optimal policy. And we saw that for small unknown MDPs, value-based RL, such as Q-learning, can also find optimal policy. And now there's the challenge of scaling up. Much of the interest in RL comes from problems with huge or even infinite state spaces. You can think of autonomous driving, for example. You have an infinite amount of states. You can think just a description of the environment around the driver in a continuous multidimensional space. So in these cases, tabular methods become unusable. It is impossible to maintain a table with infinite number of states in memory. Therefore, we need to be able to generalize to unseen states and actions. And for that, we use function approximators learned from data, which can do the generalization and approximate different components of the solution. They can approximate transition and reward functions. They can approximate value functions, and they can even approximate the policy directly. And when we use deep neural networks as function approximators, this is where we call it deep reinforcement learning. Let's see an example. So perhaps the first famous success of reinforcement learning is the TD Gammon problem. This is a backgammon playing program, RL-based. So this program has a neural network, you can see in the middle of the slide, that gets as input the board state and outputs the probability of win. In this case, the value. The value is the probability of win from this state. So TD Gammon starts with a random network. It plays millions of games against itself, learns a value function from this experience, and six weeks later, it's the best player of backgammon in the world, beating all top humans. So this created a big splash back in 1992, but it has one problem. It was very hard to reproduce in the success in other domains. So a more recent result is an agent called DQN, which is a deep reinforcement learning agent that plays Atari. The agent here represented as a brain that can output actions, joystick actions, which are then sent to the Atari emulator, which returns with a state representation as the screen pixels and the current score as the reward. So inside DQN, there is a convolutional neural network that gets these screen pixels as input, and the output on the right is 18 Q values for the 18 possible joystick actions. The joystick has 18 actions, and each one has a Q value, and that's the output of DQN. When you have these Q values, again, you just need to select the action with the highest Q values. That's very easy to do. And the most remarkable thing about DQN is that this was the first time a single RL algorithm achieved human-level results in tens of unrelated games. The only thing common between them is the input format, the screen pixels, and the output format, which is the joystick actions. And that was the first time that RL algorithm was able to transfer between different problems. As I mentioned, in these sizes of state spaces, we're not able to maintain a table. So instead, we maintain a parameterized Q function that you can see here graphically. We have an estimation using a parameter vector W. And for every state S, we can send it as an input to the function, which using, after all the parameters, computes the output as the 18 possible Q values. That replaces the Q-learning table. The way DQN works is by trying to solve approximately the Bellman equations again. So Bellman equations must hold for the optimal value function, and DQN tried to make it hold for the approximate value function as well. And again, if you look closely here, you will again find generalized policy iteration in the max operator in the policy improvement, and the policy evaluation is the computation of expectation. And without getting into all the details, you can think of DQN as a continuous extension of Q-learning. Instead of using the Q-learning update formula, we try, which assigns right-hand side to left-hand side. This time, we collect data and try to minimize the L2 loss between the right-hand side and the left-hand side. And in the specific case of Q-learning, this converges to the optimal Q function. It doesn't converge to the optimal function using neural networks. In fact, it diverges. There are several issues here, for example, that changing the parameters makes us change a moving target. But there are several tricks to solve it. We can make the moving target move slower to allow convergence. That's at a very high level. So let's see how DQN learns to play a game called Breakout. So I remind that DQN doesn't get any information about the game other than the legal actions it can take and how the screen looks like and what the score is. So initially it is not able to hold the ball for too long in the game. But as learning progresses, it is able to learn to hold the ball for longer periods in the game. And then after 600 learning iterations, something interesting happens. So what you're seeing here is a strategy called tunneling, which is considered the best strategy for this game. And no one told anything about this strategy to the agent. No one told anything about the game to the agent. And the game discovered it just through trial and error, playing against the simulation. Okay, let's go to another big success of RL, the AlphaGo program. AlphaGo is a superhuman Go playing RL program. And for those of you who don't know Go, Go is an ancient game, 3,000 years old, highly popular in East Asia. It has 40 million players. And what is important or interesting about this game, that the number of possible board positions is larger than the number of atoms in the universe. And computers that are so good at doing brute force searches are not able to do much with that number of possible positions, and it was considered even impossible for computers to evaluate who is winning. If we look at this tree of transition dynamics, so a state is a board state, a board with some stones in it, and when we add a new stone, we move to a new state, and this tree blows up very quickly. But nevertheless, the AlphaGo program developed at Google DeepMind was able to beat first the winner of 18 world titles, Lee Sedol, and then Kijai, the player ranked #1 in the world, and I think their picture says something about the capabilities of AlphaGo. So what's AlphaGo's approach? AlphaGo starts, is given nothing but the game rules, and AlphaGo, one of the versions of AlphaGo called AlphaGo 0, learns through self-play to play Go at a superhuman level. And if we look at the core of AlphaGo, we find again the good old generalized policy iteration, but this time equipped with a powerful triad of policy network, Monte Carlo tree search, and value network. A policy network is a neural network that gets the board state as an input and outputs probability distribution over possible actions. So at the top, you can see different probabilities for putting stones in different locations. This policy network represents the current policy of AlphaGo, and policy improvement is done using an algorithm called, very successful algorithm in the recent years called Monte Carlo tree search. In brief, Monte Carlo tree search is a way to search effectively in this tree of transition dynamics, to run narrow and deep searches while balancing selecting actions that are already known to have high value with actions that have high potential to have high value. So Monte Carlo tree search keep exploring better and better to learn about better and better actions. And the interaction between Monte Carlo and tree search and policy network is that the policy network is used to reduce the breadth of the search of the Monte Carlo tree search, and the Monte Carlo tree search keeps improving the policy represented by the policy network. The third component is a value network. This is also a neural network that gets as input the board state and outputs the probability of win, like TD Gammon. And this network is trained using supervised learning. For every state, we eventually know whether the agent won or lost, and we collect win and lose data and train a big neural network to be able to predict the win probability. So what we have, in fact, in AlphaGo is a powerful version of policy iteration called search-based policy iteration. AlphaGo becomes its own teacher by learning from playing against itself. We have policy improvement using this Monte Carlo tree search algorithm, some version of it, and we have policy evaluation just by the game result, the self-play game results. Okay, I would like to briefly touch on last group of RL methods that are called direct policy optimization. So going back to the agent interacting with an environment diagram, we can represent the agent's policy explicitly, for example, as a neural network that gets a state on one side and outputs some actions on the other side. And we can define this defines a parameterized policy class, and we can think of an optimization problem of finding the vector data for which the parameterized policy maximizes the expected return. Why would we, or when would we want to do that? In some problems, the policy is turned to be simpler to represent than the value function. And also, this method allows us for injecting some prior knowledge about the form of the policy. So the optimization here is, again, find vector theta that, for which the performance is maximized. And for those of you who know supervised learning, I assume many of you, you might think of using gradient ascent. The issue is that gradient ascent does not work in this case. The problem is, and again, I'm talking only to supervised learning people, I know that this won't be clear to everyone, but the problem is that it's not possible to backpropagate gradients through these dynamics because some of the dynamics are unknown, the red parts. This is in fact the transition distribution, the distribution of moving to next state. But there are solutions to that, and many solutions try to estimate gradient from samples, and there are different approaches for how to do that. But even with these approaches, it can still be pretty hard to get to work right, this direct policy optimization. It has at least two other issues. First, it's very hard to choose a step size, and in reinforcement learning, choosing bad step size could be much more detrimental than in supervised learning. And it is highly inefficient, sample inefficient. This means that it doesn't use the data efficiently, and therefore it requires huge amounts of data. Luckily, there are several tricks that can significantly improve the situations. For those of you who heard about the terms baseline, KL divergence, and importance sampling. And there are also some nice theoretical results that we can modify the objective and get lower bound on performance. And in fact, these ideas are at the core of proximal policy optimization algorithms proposed by John Schulman recently. And one of the successes of these algorithms is learning dexterity. So here we see a robotic hand trying to manipulate a cube to get to some goal state given to it. And what is remarkable about this hand is, again, no one programmed any of its behavior. It was learned completely from trial and error in simulation. And that's even more remarkable or more exceptional. Using simulation to learn allows us to get lots of data because we can run many jobs on computing cluster. The problem is that typically something that was learned in simulation does not transfer to the real world because of the discrepancies between simulation and the real world. And here, using several clever tricks, they were able to enjoy the lots of data they can get from simulation and apply it as is in the real world. Okay, so before I conclude, I want to give some credits to some guys whose slides contributed to this talk with their kind permission. So my colleague Shivaram, my advisor Peter Stone, and also Rich Sutton, Dave Silver, and Dan Klein. And for those of you who are interested, there are useful resources online. First and foremost, the book of reinforcement learning by Sutton and Bartu, and also some great online courses such as Introduction to Artificial Intelligence by Dan Klein and Peter Abil at Berkeley, and some other RL courses by David Silver, Sergey Levin, and Peter Abil. Okay, to conclude, in this talk, I focused on mainly on robotics and games, but in fact, RL's applicability is much broader. It applies to a wide variety of applications. Only some of them, a small fraction is listed here. At a high level, some of them are environmental applications like renewable energy management, smart homes, even wildfire suppression, financial applications such as portfolio management, pricing optimization, autonomous trading, and also system optimization, many problems in the Internet of Things, computing cluster optimization, logistic and delivery, and many, many others. And the important point to remember is that RL applies to any problem that involves optimizing sequences of decisions over uncertain outcomes. So to summarize, in RL, we do not program behavior. Instead, we specify goals. RL is autonomous learning to optimize sequences of decisions and has huge potential real-world impact. And the current status of RL is that following exciting academic advances, RL is now taking off in industry. But there are still lots of exciting research fronts, and we're still far from completely solving RL. There are no off-the-shelf toolbox solutions. And in fact, successful application of RL frequently requires high degree of expertise, creativity, and even innovation. In other words, what I'm saying is that we still need human intelligence to create superhuman RL applications. So I hope that in this short talk, I've convinced you that RL is a very promising technology, and I can tell you that it is changing the face of AI right in these moments. Thank you for your attention, and I still stick around today. I think we have no time for questions, but I'm happy to talk offline. I'm here. Please feel free to approach. Thank you very much.